Hi, welcome to your lesson on rates of growth and decay. So we've already looked at exponential growth, which always has this kind of shape when graphed. All right, and these are examples of exponential growth functions. Some base and the x, the variable, is the exponent. We've also looked at exponential decay, which looks like this, falling quickly and then slowly, approaching this asymptote. And those functions look like this with a negative exponent or a value that is less than 1 or between 0 and 1 as the base of this exponential expression. So let's take some notes in your notebook this time. We're going to do a couple problems and look at some things. But before going to the notes, actually, let's look at Desmos. I have something ready here to show you. There's something important that hopefully if you did the investigation in class last time you discovered. So here is an exponential function. Notice this is a little different than the one we just saw in examples. There's this other parameter in front here. It's called the a value. So here's our actual exponential function, 3 to the power x, but in front of that we have another value, a. So let's see what happens when we vary a. All right, so let's put a right here, for example. Notice how this went up. A value is 2, and look at where this hits the y-axis at a value of 2. Now I'm going to make a 0.7, and it hits the y-axis at 0.7. And as I keep going, notice the a value determines what the y-intercept is. That's an important thing to know about exponential functions. If there's that parameter in front of the actual exponential expression here, that parameter controls where the y-intercept will be. All right, and that is also known as the initial value. So remember that if there's a number in front of the exponential expression here, that number is like your beginning number, because usually the y-intercept is called the beginning number or the initial value because it occurs when x is 0. All right, so remember that the a value is the initial value. Let's go back to here. So now taking notes, there are two main models for exponential growth and decay. There's the growth model, decay model, and these are just a kind of a different way of writing what we've already had. So here we have y equals a, and then in parentheses 1 plus r to the x power. So this is exponential, we can see the x there. We can see that a in front, so that is again called the initial amount. All right, so there's your initial amount, then you have some base of your exponent and x. So and decay is the same thing like that, but it's 1 minus r. And then there's the x, and there's that initial value there as well. So r is called the growth or decay rate. It's often given as a percent. So r is your rate of growth or decay, and x is usually the number of time intervals for these kinds of relationships. So please definitely add this to your notebook. We'll be using these models to solve all kinds of problems. Going back to Desmos, and what happens then, that number here in the middle there, that was like our 1 minus r. So let's say, or 1 plus r, I'm going to make r a slider. So r value is like some percent rate, right? So look, if the r value is 0.5, this becomes 1.5. All right, so we have exponential growth. But if the r value is negative, then this becomes, here, for example, r is negative 0.4. This would be 1 minus 0.4, which is 0.6. So that's like a decay. All right, so when you do 1 minus something, you're going to have exponential decay because this becomes less than 1. But when you have 1 plus something, see the r value is more, 1 plus something, then it's going to be growth because it's going to be 1 point something, and it's going to mean that something is growing. All right, so that's how our model works. It's just like a normal exponential, but now it has this 1 plus r here representing whatever that base is. All right, let's look at an example problem. The population in the town was estimated to be 38,000 in 2015. Since then, the population has increased each year by approximately 2.4%. So that's like our R value, our rate of growth or decay. In this case, it says the population is increasing, so this is going to be a growth problem. All right, we're going to use this model. Our rate is 2.4%. So we've done some problems like this as well. We were trying to figure out these kinds of problems the other day. When you have a growth rate of 2.4%, you have to convert that to a decimal. And the first question here says, what is the growth factor of the population in the town? The growth factor is going to be this entire thing, 1 plus whatever the rate is. So the growth factor will be 1 plus r. That means 1 plus, there's the decimal for 2.4%, it's 0.024. So our growth factor is 1.024. So if you're saying, here's my initial population and I'm going to make it grow, you would multiply it by this number, So here it's your initial amount, A, it's going to be multiplied by this number, and that will give you how much the population is growing, right? So that's what the second question is saying. Write a function to model this population growth. So here's our model. We're going to use this growth model. Y equals the initial amount times the growth factor, which is 1 plus the rate, which was this here, to the x power. That means 38,000 you'll multiply by this number, and that means 38,000 will grow to 1, which is itself, plus that extra bit, which is the extra bit that the population has grown. So we're going to end up with a figure that shows us the new population. All right, C says, use your function to estimate the population to the nearest 100 people in the year 2030. All right, if this started in 2015, then 2030 is 15 years in the future. So that's what this calculation is here, 15 years. So the value we're going to put here, the time intervals, is 15, because 15 years have passed. So basically we have our initial population multiplying that by this growth factor, and we're doing that 15 times because every year it grows that much, it becomes a new number, then you multiply by this amount again, and it becomes a new population, and then multiply by that again, 15 years in a row, you're multiplying each amount as it grows. So our final population is this. All right, let's look at problem number 2. Sarah bought a car for 15,000. Its value depreciates or loses value by approximately 15% each year. So what do you think the depreciation or decay factor is? This time it's going down, so we're going to use a decay model. And now it's 1 minus r, right? Because we want this value, once we've multiplied the initial value, which is going to be the 15,000 right here, we want to multiply by some number. And we don't want it to go up, we want the car value to go down. So this number we're multiplying by has to be not greater than 1, but less than 1 in order for this to go down every year. Right, so this has to be less than 1. So what's your depreciation or decay factor going to be? Well, decay factor is 1 minus r, so 1 minus 0.15 is the 15%, and we get 0.85. So this portion here is going to be 0.85. So what's our function for the future value of the car? Our function is this. We have the initial amount, A, then you multiply by the decay factor, which is this, 0.85, and then to the x power. So now use your function to estimate the value of Sarah's car after 3 years. So use the model, 15,000 times this amount 3 times, because first year you'll multiply by that amount, and it'll give you a new value for the car, which is going to be less than 15,000, because we're multiplying by less than 1. Then next year you're going to multiply by this again, because it's going down in value again, and then a third time. And there's the value after 3 years. Great. It's important that you practice these skills. There's an assignment linked on the website. It looks something like this. The answers are given at the end. There's even this great problem about an insect right here. Let's get you started on this assignment right now. We're going to look at the first 2 problems. So here's the first problem. It says for each exponential function, identify 1, or I, the growth factor or decay factor. Whoa, let's go back. Yikes. All right, the growth decay rate and the initial value A. So make sure you understand the difference between the growth decay rate and the growth decay factor. The factor is the entire amount. The rate is the actual percent rate. So here, what is our growth decay factor? Well, it's 1.43, but the rate of growth is 0.43 or 43%. Over here, it shows you a number less than 1, so it must be decay. So the decay factor is this number here. But the decay rate, how much is it going down every year? If this is your factor here, how much has it gone down from 1? Let's take a look at that. So that one is, there's our factor, but there's our decay rate. The percent of decrease was 38% because you did 1 minus that 38 to get this factor here. All right, here we have 2/3. So again, that's a number smaller than 1. So that tells us that this is a decay problem. So this number is obtained by doing 1 minus r. So this is our decay factor. So if you look at that, they give you that 0.667 is the same as that, 2/3. So that's our decay factor. But the rate of decay is 1 minus r. So what is that r value? 1 minus this, sorry, 1 minus what gets you this, and it's 1 minus 0.33, which is 1/3. So 1 minus 1/3 gets you that, so the rate must be that. And the last one here, we have an A value, the initial amount, and here's our factor. So our factor is 1.2, so it shows that it's a growth factor because it's bigger than 1. So 1 plus R is what gives you this number. So then second problem, what is the actual growth rate? The growth rate is, well, 1 plus R gives you this, so the rate must be 0.2, because 1 plus 0.2 gives you 1.2. And oh, I didn't answer the last question for all these. It says find the value of A, which is the initial value. This one, the A value must be 1 because there's no number in front, so it must be 1 times this. This one has that 3 in front, so that's our A value. There's a 4, and there's a 0.8 as our A value. So take a look at those. Make sure you understand the difference between that and that, this and that, this and that in every question. All right, this problem you have to try. We have a jeweler who estimates that the value of gold is increasing by 12% every year. You have to find a growth factor. You have to write the model, and then you have to estimate the value of the bracelet in the year 2030. All right, give it a try. So our growth factor is 1.12. It's 1 plus R, 1 plus that, which is 0.12. Our function is this function, our initial amount, times the growth factor to the x power. And then when you look at 2030, that's 15 years from here. So I guess 15 was put in here, and that gives you this value of the gold bracelet in the future. All right, please try the rest of the practice problems. You can do it. Try some more right there.